Dear friends, dear colleagues, welcome to our seminar on optimization. Today, we have the pleasure to have a speaker, Mert Pilanci from Stanford University. So Mert obtained his bachelor degree and his master degree from Bilkent University, probably one of the best or the best university in Turkey. And he received his PhD degree from University of California, Berkeley in 2016, and his studies were supported by a PhD fellowship of Microsoft Research. So after his PhD, he was a postdoctoral fellow with Emmanuel Candes at Stanford University. He then moved to the University of Michigan, and then from Michigan back to the Stanford University, where he is now on the position of assistant professor. Mert is working in many interesting topics, cost optimization, but as well as signal processing, at the intersection of these topics. So Mert, thank you for accepting our invitation. You have 45 minutes for your talk.
Thank you for the nice introduction, and thank you so much for organizing this great event. It's a privilege to talk to this crowd. So I'll be talking about our recent work from our group on convex optimization methods for deep neural networks. Interestingly, neural networks are not close to convex optimization at all. Actually, the neural network training problem is one of the most important non-convex problems studied in the literature. But it turns out that there is a formulation of these problems when the activation function is the ReLU rectified linear unit. And I will talk about that. I will first talk about our basic result on ReLU networks, and then I will introduce extensions, deep networks, and other methods. Neural networks have a quite rich and long history. I will not go into that, but essentially the artificial neurons were invented around 1940s. Then AI entered into a dark age because at the time people were convinced that neural networks are quite hard to train. They are non-convex optimization problems. And they did not have the resources to train them like the GPUs we have now. And from the theory side, they were also convinced that two-layer networks will fit any function. They are universal approximators, but they will be quite hard to train, and they were quite discouraged. When I first learned about neural networks around this early 2000s, neural networks were quite unpopular. In fact, convex optimization, compressed sensing, L1 regularization methods, they were more popular than neural networks. But at around 2012, there was a complete paradigm shift. We have witnessed the deep learning revolution. These are essentially very deep neural networks trained with very, very big data sets. This is showing ImageNet classification challenge error results. As they get deeper and deeper, they started performing better. And these days, they can have a couple hundred layers. They can have trillion parameters in them. And they made tremendous impact in computer vision, self-driving cars, robotics, playing games, reinforcement learning, audio processing, video processing. We have witnessed the impact in everyday life. And moreover, they enabled doing things we did not have any way of doing before. We have no way of imagining how we can, for instance, generate realistic images. So the people you see here are not real people. They are just generated by neural networks. So for realistic image generation, deep networks set the state of the art, and we have no other competing method. So I will first talk about some challenges in neural networks that exist today, and I will introduce our model, training ReLU neural networks with convex programs. Then I will tell you about extensions, such as deeper models, generative adversarial networks, and some other applications like autoencoders. So deep neural networks are usually trained with local methods. The most famous method is stochastic gradient descent, but these are extremely high dimensional problems. Typically, they will contain millions, billions parameters. And as you can see, the training is a bit heuristic. You don't get the global optimum. You just initialize randomly, do gradient descent steps, and then hopefully be near a stationary point, right? And then in practice, this seems to work quite well. And it is a bit puzzling why this works, because it's against many other things we know in optimization. Non-convex problems are quite hard to solve. And there are lots of challenges associated with that. First of all, the training problem is quite hard to solve. An example is this GPT-3 language model. It costs $12 million to train this model. A single training run costs this much. And also quite large data sets which are not public. From the academic side, it is quite hard to compete with big companies in terms of the finance and also finding the data sets. And another problem is interpretation. Deep neural networks became black box systems because you just run a black box training algorithm like gradient descent, and it does have trillions of parameters. We don't have ways of interpreting what the model is learning, right? We don't know what happens with gradient descent, what kind of information is captured by the neural network. And this is very different than convex optimization models. In fact, I will give you an example very soon. So here's an interesting recent result from the deep learning literature. This paper was published in the journal Nature. It's about predicting aftershock patterns after big earthquakes. The authors in 2018 proposed a deep learning method that does much better than state-of-the-art for predicting aftershock patterns. Interestingly, 1 year later, a different set of authors published in the same journal a different paper showing that logistic regression actually performs just as good as this deep neural network, right? And this is quite strange. The first authors did not even consider a simple model like logistic regression, which is actually a one-layer neural network. Well, things like this actually keep happening. There are places where deep learning definitely works better, like computer vision. And there are places, there are topics where people just apply deep learning without trying out other methods. And because of the hardness in interpretability, the literature is a bit unclear, right? Deep learning doesn't always work better. One interesting question is asking, what does the neural network do, right? It is hard to understand. And I think that's because of non-convexity. Another example is from medical imaging. This is from the fast MRI medical magnetic resonance imaging challenge. So it's been shown that deep neural networks actually reconstruct images much more accurately, but there might be some problems. They can hallucinate sometimes textures. For instance, this vessel is a false vessel, meaning that it is not in the true image, but it is basically hallucinated by the neural network. Since it sees tons of images like that, it can actually memorize textures and patterns, and it can reconstruct it with that hallucinated texture. Of course, this is unacceptable, right? And simpler methods like convex optimization-based reconstruction methods, they don't do this because they're quite simple. Maybe they don't work as accurately, but you can trust those methods perhaps better. Another interesting fact with deep neural networks is that if you perturb the input to these deep neural networks, you can actually change the output in any way you like. People call these adversarial examples. If a network classifies an image correctly, you can find a perturbation so that it will be classified wrong. And these examples even happen in practice. If you have a stop sign and you put certain perturbations on it, in this case, this black and white tape, it will be recognized not as a stop sign, but a speed limit sign. These are very concerning, right? So the questions I would like to answer are the following. What are neural networks actually doing? They are doing something else than convex optimization methods, classical machine learning methods, but can we identify what they are really doing? Are they automatically finding the best features? Are they finding the global optimum, a local optimum? And probably there is a more efficient way, because if you look at the deep learning literature, almost every month, people are coming with new architectures that are doing better, transformers, mixer models. They have not converged to the right architecture. Maybe by understanding what they are doing, we can design better learning architectures. That's the ultimate goal. So how do they really work? Here's a fun example. So we have this book. I have a 2-month-old daughter. Well, she doesn't particularly like this book, but I read this book to her sometimes, Neural Networks for Babies. And even this book shows how a neural network works and how it is trained. It's actually quite simple. So it shows here you You just grab a big chunk of data points, patterns, you show them to the neural network, and then it learns, and then you test the neural network, right? It does something. And I think the rest of the literature on neural networks are not providing any better explanation than this book, in terms of how they work and how they're trained. You just show them a list of patterns, and then it will learn something, right? And this is a bit unsatisfactory. I think we should have a better answer to how they really learn things. In convex optimization, actually, this is very clear. If you look at least squares optimization, logistic regression, support vector machines, we have absolutely an idea of what they are learning and how they are learning. And moreover, what they learn is independent of the solver. If you have a convex problem, you can apply any solver, first order, second order, and they will find the same model. In non-convex optimization, it is a bit complex because there are multiple local minima, stationary points. Now the solver actually influences what the model you learn. In fact, solver is inside model parameters. You cannot decouple the solver issue than the modeling issue, right? Because of that, we don't have insightful theorems for neural networks. So what do I mean by an insightful theorem? Let me give you an example. I think an insightful theorem is the following. Let's say you have a least squares optimization problem, minimize the norm of ax minus b with respect to x, right? Very classical problem, quite important in many disciplines, statistics, control theory, machine learning, signal processing, right? The interpretation is that you're trying to find the closest vector in the range of A to B, right? And it is a projection onto the range of A. And actually, this is clear from the first order optimality conditions. If you set the gradient to 0, it's a convex problem. You find the global optimum, which reads A transpose AX equals A transpose B, right? And you can also interpret this. In statistics, people say this equation, call this equation normal equations, right? Or orthogonality, which actually shows that if you have noise in B, the prediction you find is orthogonal to the range of A. So the model uncertainty is only in the subspace perpendicular to the range space of A. And moreover, because of our basic knowledge, fundamental knowledge about this problem, we have very efficient solvers like conjugate gradient or QR decomposition, Cholesky decomposition based direct solvers, right? No one actually should apply stochastic gradient descent if you have conjugate gradient, preconditioned conjugate gradient, QR decomposition readily working fine. It's giving you exact answers, right? Maybe for very large scale problems, you can apply stochastic gradient descent methods, right? But we have much more efficient software, and people actually use more efficient, reliable software like that for least squares problems. Another interesting problem is least squares with L1 regularization. So what you do is you add a term here, which is the sum of absolute values, L1 norm, and then add a multiplier lambda. This is called lasso in statistics. So what this does is it finds you a sparse solution. It makes the coefficients of x mostly 0. So in statistics, what this does is it identifies the columns of A, which are relevant in predicting y. So it is quite useful, of course, to find relevant predictors. And there are more sophisticated versions. For instance, you can have a vector x and you can divide it into groups. And if you want sparsity over these groups, meaning that you want most of these groups exactly 0, you can change L1 norm to what's called group L1, which is sum of L2 norms of these groups of variables. And the solution will have most groups 0. And this is called group lasso, also used in statistics a lot to discover groups of predictors which are relevant. So let's look at a neural network problem. And let me describe you our first basic result on convexity of neural networks. So let's say we have a 2-layer neural networks with rectified linear units. A rectified linear unit is this function, basically a ramp function. And earlier in the neural network literature, people were using unit threshold, unit step activations, and then sigmoid activations to approximate them. This was one of the key discoveries in the development of deep learning. Actually, ReLU activations enable training deep neural networks. But there's not much known about why it really works better than other activations. The convex optimization side actually shows a good reason for that. So this problem is non-convex. We are minimizing with respect to two layer weights, W1 and W2, okay, first layer and second layer. So this phi is the activation. L is some loss like squared loss. Y are the labels. And then we have this regularization, which is standard sum of squares. L2 norm in the parameter space. The most standard formulation of neural networks training problem is this one. And of course, a non-convex problem because of the multiplication with two layer weights, W1 and W2, and also the activation, nonlinear activation phi. So it turns out there is a convex optimization problem, which will have a matrix variable Z and some convex regularization R applied to Z. So this second problem will be a convex optimization problem, and we can solve them to global optimality. It turns out that the two values are identical, and you can find the solution to the non-convex problem from the convex optimization problem. If you solve the second one, you can generate the optimal solution to the first non-convex one. This is our first result in this topic, and it shows that actually there is a parameterization that will make the neural network problem convex, and we can use that to get the global optimum. So one thing to note here is the dimensions here. So this matrix Z is it's a D by P matrix. And I will show you what this dimension P is. This P is bigger than the dimensions here, okay? And you can think this result in terms of the lifting approach in semi-definite programs, if you have heard about those. Essentially, in a higher dimensional space, a non-convex problem can actually look like a convex problem.
May I ask about this formulation? What would be the space of matrices associated? What is the K?
Oh, okay, I will show. Yeah, I will show all of them in the next couple of slides.
See. Sorry. Yeah.
Okay. Any other questions? Okay, good. Let's go ahead. I will show you explicitly what these sets are. And we will look at a simple example just for the sake of notational simplicity. So let's say this is our data matrix. We have n examples of dimension D, and we have labels. Assume labels are scalar. So we are in a regression setting, just like least squares regression. So the neural network training problem is this one, right? So this is the neural network output. We have a sum over hidden neurons, right? And then this is the regularization for Frobenius norm squared, sum of squares of all parameters. The convex optimization problem here is the following. Okay, so the loss is the same. We have the squared loss. The variables are UI and VI, okay? So there are these matrices DI. I will tell you in a later slide what these are, but these are fixed matrices. We can compute these matrices from data, and they are diagonal. And the regularization is, interestingly, sum of L2 norms. This is the group L1 norm. And what this does to the solution is, it actually sparsifies the solution. It gives you a solution that is very sparse, and that is controlled by lambda. This lambda is exactly the same lambda here. It is the coefficient of this regularization. In neural network literature, people call this the weight decay regularization. It's just L2 norm regularization. That's also used in least squares. So if you solve the convex optimization problem, there is a closed form normalization here, which will give you the optimal layer weights, W1 and W2, in the non-convex problem. And there's a one-to-one correspondence between these weights. But this problem is convex, essentially. It's just least squares with some convex regularization, right? And by looking at it, actually, you can see what this is trying to do. It is trying to explain why, in terms of few of these variables, UI and VI, you want as few UI VIs as possible. Same as in lasso and group lasso. And I will tell you what DI matrices are. As you can see, it just multiplies the data from the left, and they are 0, 1. I will show you what that is very soon. Before that, so let's think about what happens if you choose a very small lambda and a very large lambda. People call this a regularization path in the lasso literature. As you scan over lambda, you will get a solution path with different number of non-zeros, right? It turns out that if you scan over lambda and if you solve all the solutions, it will give you the entire set of optimal architectures with different number of neurons, because this lambda actually controls the number of non-zeros and the number of neurons you can actually transfer to the non-convex problem. So an architecture search in the non-convex optimization, meaning you try out lots of different hidden neuron values, is identical to a regularization search in the convex optimization domain. And this correspondence was in fact not known before. So in this sense, non-convex neural network models, they correspond to regularized convex models. Essentially by dialing in the number of neurons in a hidden way, in a latent way, you're controlling the regularization by picking some lambda. Okay, so what are these DI matrices? I will try to describe what they are geometrically. So let's say we have 3 samples, n is equal to 3 in dimension 2. So our matrix X is 3 by 2. Let's say the consists of these points, 1, 0, 2, 2, 3, 3. Labels are Y, they don't matter. So let's look at a hyperplane, and we will encode which points are separated by this hyperplane. And you can pick one side, like the positive side of this hyperplane. And we will encode it as 1, 1, 1 on a diagonal matrix. Okay, so the D1 is this 1, 1, 1 identity matrix. D1 times X is that matrix times the data matrix, which is the same as the data. Okay, if we change the hyperplane, we will get a different separation, right? We will get pattern 1, 1, 0, indicating this one is left out by the hyperplane. And D2 times X will be the data matrix with the third row zeroed out. Okay, and we will enumerate all these possibilities. There's this one, which will give you all zeros, and then there is this one, which will give you 0, 0, 1. Okay, so there are actually 4 possibilities. One is completely 0. So the neural network problem will have an exact convex programming formulation in this case, which is the following, right? So here we have D1x, D2x, D3x, and they are just data matrices with masked rows, right? And we have this regularization and some linear constraints indicating which side of the plane these samples are. And as you can see, this is a very simple convex program.
So if we have a question, Mert. So
okay, I can read it.
Yes.
So the question is P convex continuous in lambda on slide 24? Alternative phrasing is the Pareto front of the objective and lambda a connected set. Okay, very good question. So if we change lambda and if you look at the optimal set, I think it is, yes, it is connected. It is continuous, but not differentiable. It's very similar to group lasso in its optimal solution set. I think so. I'm not 100% sure, but I think that is a connected set that is continuous. As you change lambda, what happens to the optimal set? Another question is why you state UI minus VI, not UI? Okay, that's another good question. So it turns out we need this difference UI minus VI to represent negative second layer weights. It's essentially a technical thing, but it turns out we need to have both. If you drop one, I don't think that the theory will work.
No, but you could reformulate it just by using UI there and introducing a new variable. Yeah, but then.
Oh, that's right. That I can do. Yes, you're right. I can call this UI prime and then change this regularizer to, yes, you're right. Yeah, maybe that is simpler. You're right. Okay, thank you. So this is going to be the convex program for the ReLU neural network, right? And actually at this point, you can interpret what this is doing. So if this Y vector is actually explainable using any of these local so-called models, right? Local, meaning that we have this model local to data point 3, and then it zeroes out the first 2 samples, right? If this is very predictive, this will actually get selected. So if you know about lasso, how it works is that if there's a column that will explain why, the first non-zero solution will be that one, right? And actually it is trying to find a very concise local model, right? It's trying to find a mixture of such data local models that will explain why. Okay, makes sense. There's one more question. VI represents deleted term by ReLU. Oh, actually, UI and VI, they both represent hidden neurons, like in here. So they represent hidden neurons. A 0 here means that is actually killed by ReLU. Or this 0, right? So this means these are killed by ReLU, or this one. And these actually, they pass exactly through ReLU. And this is actually what's special about ReLU networks. If you had sigmoid activations, they do strange weighting, strange windowing to it, right? But ReLU is very special. It only passes through or it blocks it out. It acts like a filter, right? And probably that's the reason why deep learning methods started working when they switched to the ReLU activation, not with sigmoid. These are essentially convex models. But people use the non-convex parameterization of these convex models, in my opinion. Okay, so
Mert, I have a question. Could you please go?
Sure.
Okay, so is this a set K, calligraphy K? So this
yes, that's okay. Right. So in my first slide, I had something like K describing these sets. You're right.
Okay.
Right.
Good.
That's K.
Yeah, thank you.
So this is a way to actually understand deep neural networks in terms of convex optimization. It is as if we have some data. What the neural network model does is it applies some embedding to the data, right? So that we map the data to high dimensions by multiplying with these masks, D1, D2, DP masking matrices. So we get a high dimensional representation of our data set. And the neural network is a convex regularization method applied to the data, right? Another question from the chat is, how do you choose the hyperplanes? Okay, very good. So in the theory, you have to look at all possible enumerations of these separation, right? In this case, we only have 4. We have only these 4 ones. The ways you can separate the data by a hyperplane. As you can see, it is a finite set, how many combinations I can have that way. And I will show you how many that number is. It actually controls the complexity of solving this problem. Turns out, training a 2-layer ReLU network, if you do it brute force, is actually very hard. Why? Because you have this ReLU activation here, right? It is on or off, and you have to search over all on-off patterns. And you have M such ReLU neurons, and you have N data points. So the combinatorial brute force search will have complexity to the M, because you have M neurons that you have to switch, you have to search over, right? And to power DN. Turns out this is the best complexity if you do it brute force. And this is actually not doable because even with 100, 200 neurons, this will be very, very high. The convex program in comparison, it does the same job. It globally optimizes the neural network in complexity order and divided by R to power R, where R is the rank of your data matrix. Okay, now this is interesting because we have to be careful not to break down complexity theory. If N is the number of samples and D is the dimension, the complexity is going to be polynomial in N if R is a constant, right? So if you have a data matrix with fixed rank R and the rank is constant, this is a fully polynomial time algorithm. And this includes a fixed dimension. If you fix the dimension, it will be a polynomial time algorithm. But the complexity is worst case exponential in D because this rank can be full, the rank can be D. And turns out this cannot be improved unless P is equal to NP, even if you're fitting just one neuron. It has to be exponential in D. So we are not breaking down complexity theory, but we are actually improving the results exponentially. And we can actually solve these convex programs in practice. So where does this number come from and divide by R to power R? It turns out this is exactly about the question someone asked, right? How many combinations I can have, how many different possibilities I can have in terms of data separation by a hyperplane. These are called hyperplane arrangement patterns. We look at the sign vector of some matrix X times a free variable W, and as W changes, we get different sign patterns. This number is actually at most this much, which is bounded by N divided by R to power R. So essentially, if you have hyperplanes with normals, xi, rows of x, these are the number of chambers you can have in this arrangement of planes. Okay. But isn't this a very big number? Well, it is big, but in practice, actually, what works best are convolutional neural networks. And if you have a convolutional neural network, the number of arrangements is actually very few. It will actually be always polynomial. So it turns out if you have a convolutional neural network, the right thing to look at now is a patch of the data, right, multiplied by a weight, which is called convolution. And if you look at the sign patterns of convolutions, it is actually always polynomial. As long as you have a filter of fixed size, you will have a polynomial number of patterns. And these can be optimized in fully polynomial time with the Convex program. So this enables actually optimizing CNNs, convolutional neural networks, in fully polynomial time for the first time. And these are actually used quite widely in computer vision. And you can actually train them in sequence. If you train a 2-layer convolutional neural network, you can train one more, and then you can actually stitch them together to create a deep neural network. If you want to approximate these patterns, actually, this is also quite easy. How we can do this is, this DI matrices will be approximated by sampling them randomly. We sample a random vector U, for instance, from a normal distribution. And then we look at x times u greater than 0, this pattern, right? This will be one of the DIs. And we can do essentially Monte Carlo, sample lots of such patterns, and then solve the Convex program, which is essentially a coordinate descent type approach, optimizing random blocks at a time, essentially. It is a random coordinate descent applied to the Convex program. Another option is you form a low rank approximation to the matrix. And the low rank approximation will have actually very few patterns, at most this much, but it will give you an exact approximation, an approximation with an exact upper bound, which will be in terms of the smaller singular values. And also you can see backpropagation method, the classical local search method, backpropagation with gradient descent on the non-convex loss as a heuristic for the convex program. Essentially, it is an active set type method. Active set methods in convex optimization, they optimize a few variables at a time. And backpropagation exactly of that nature. It actually has a set of neurons. These are working variables, which are like some patterns sampled from the set. It optimizes over them, and actually it can switch which variables are active. And recently, we were curious whether the convex optimization problem gives you one particular global optimum or all of them. And we were able to show that the convex program actually gives you all of the optimal solutions. Essentially, if you have this non-convex problem, all optimal solutions can be generated from the convex program. And this can only happen up to permutation and what we call neuron splitting. Permutation is just changing the order of hidden neurons because it doesn't change the objective here. It creates the same point in the non-convex landscape. And there's something called neuron splitting. If you take one neuron, you can write it as 2 neurons, essentially. If you have X transpose W plus as a hidden neuron, you can write it as simply this times 1/2 plus the same times 1/2. And this actually counts as a different parameter point in the non-convex formulation. And turns out these are the only 2 ways you can actually have other optimal points, permutation and neuron splitting. And let me show you some experimental results. So here we have different trials of stochastic gradient descent method with different initializations. And we look at the training objective value, and we solve the convex program, and we plot the optimal value by a straight line. As you can see, stochastic gradient descent sometimes finds the global optimum, converges nearby global optimum, and sometimes it is stuck at local optimum or stationary points here. And as you increase the number of hidden neurons, actually, stochastic gradient descent is more likely to get near the global optimum. This is a small set. A small training set. With a larger training set, actually, what happens is, because of the conditioning of the problem, stochastic gradient descent never reaches exactly the global optimum. Here we see a gap. Maybe if we run it longer, it might reach, or maybe there's a local minimum near the global optimum. But with the Convex program, actually within reasonable time, this cross marker shows the time it takes to solve using a standard solver to solve the problem global optimally. Interesting thing is, if we get a better training objective value, what it translates to in test accuracy is better, interestingly. So by optimizing better, actually the test accuracy gets better compared to the non-convex heuristics. And this is done on CFAR dataset, image classification, binary 2 classes. And in the CFAR dataset, now we are looking at 10 class classification, and we are trying out something different. So we have a convex program. We can also apply SGD to the convex problem, right? Just like people apply SGD to the non-convex problem. Turns out, if you apply it to the convex problem, it is actually more stable. And the blue curve shows the training accuracy here of the convex problem. And then red ones are SGD applied to the non-convex problem with different step sizes. The convex objective actually with a fixed step size is optimized better due to convexity. And you reach slightly higher test accuracies in the convex program. So in the rest of the talk, I will show you some extensions of this result and some other numerical results as long as time permits. So I'll talk about autoencoders, generative adversarial networks. But first of all, if we have an autoencoder type neural network, the interesting thing is the thing we're predicting is a vector, usually the input itself, right? So the output of the network should be a vector of the same size. And turns out in this case, we can also derive a convex program. The only difference is the regularization changes from sum of L2 norms to sum of nuclear norms. And what this does is, it finds a mixture of local models, which are low rank. So this sum of nuclear norm penalty does two things. It makes most UI 0 because it's a block regularizer, just like sum of L2 norms. And also each individual UI becomes low rank, right? A question from the chat is it possible to compute the convex optimum cheaper than calculating the optimizer? So it can serve as a stopping criterion for the non-convex optimization. Yeah, I think so. I think it can be done cheaper. Yes, an interesting aspect is, which we haven't realized, the solution is quite sparse, and we should have better methods. That leverage the solution is quite sparse. If you look at the solution, it will be quite sparse, just like Lasso. We are using standard solvers right now, but there can be specialized solvers. With those, it will be much cheaper.
So standard solvers are like ADMM or Chambol, POC, primal dual solvers, or this type of methods?
Oh yeah, we use interior point methods at the moment. We use mosaic solvers usually.
Okay.
Yeah, mosaic interior point solvers.
Okay, probably there are much better methods to use here, like proximal, like methods which evaluate the one norm through prox operators, and then then you have some composition between operators. You can do some primal dual, use some primal dual techniques. I mean, there are probably much better methods to use.
Exactly, I agree. Yeah, we haven't explored, but they will be more efficient. I totally agree. Another question from the chat is, if P convex and P non-convex yield the same optimal value? Yeah, that's true. Do they have the same dual programs? Oh, okay, good question. Actually, very good question. So the question is, if you take the non-convex problem, take the dual, there will be a duality gap, right? Is it the same as the dual of this convex problem? Actually, the answer is no. If you take the dual of the convex problem, you get something very trivial. And there's really a large duality gap. So we take how we compute the convex program is we first reparameterize the non-convex problem. Mm-hmm. And then the dual makes sense. Yeah, very good question. It's about actually changing the regularization a little bit by doing the scaling. If you do that, then the dual will match the primal. There will be no duality gap. But as it is, the non-convex problem has a trivial dual, meaning the dual Lagrangian duality gives you a trivial convex program. Another question is about optimal objective value being. Oh, I see. Okay, I think sorry. The question was, or the earlier question was about whether the optimal value can be computed cheaper than solving the problem. Okay, that I do not know, but it is possible. I think it's possible. At least we know upper and lower bounds on the objective are quite easy because we have the dual problem, right? Any feasible dual gives you a lower bound, which is actually quite nice, right? It's very hard to get a lower bound on a non-convex problem. It is extremely hard, right? Getting an upper bound is easy. Any feasible solution will give you an upper bound. So my answer is yes, I think it will be very easy to get bounds on the optimal value, upper and lower bounds. You get one from the dual and one from the primal. Yes, and then you can use these values to find whether you have reached the global optimum in non-convex optimizers. That's also right. Okay, so another extension we have is using batch normalization. So this batch normalization was a very critical technique in deep nets to become very, very deep. A batch normalization is actually a layer that is optimizable, has two parameters, alpha and gamma. So what it does to the input is it first subtracts the mean, okay, and then normalizes the variance to 1, and then has this trainable parameters, multiplies with gamma and adds alpha. So you just normalize it, 0 mean and unit variance, and then actually allow it to alter this normalization back, right? Take it back. And then you train alpha and gamma. So it turns out, very interestingly, if you add this batch normalization after ReLU and train all parameters now with standard regularization, there's a convex program, which is the same as before, okay? But what changes is we have UI here instead of DI times X. And what is UI? UI is essentially the DI X from before, SVD'd, and you take the left singular vectors. So in other words, applying batch normalization here, it whitens the data, but locally, you take DI times X, which is a local data partition, right? And then you apply SVD and you take the left singular vectors, which is white. That is, it satisfies UI transpose UI identity, right? So this actually does a very familiar trick in machine learning. You apply whitening so that you have better landscape and also you have better generalization properties. And with batch normalization, actually neural networks learn better, right? And we show that this version of the convex program does better, and it does also better than the non-convex version of batch normalization. We have been getting comments about our work, and some people were arguing that regularization is not really important. So if you look at my results, it depends on the regularizer, which is sum of L2 norms, right? In the non-convex formulation, it is the sum of L2 norm squares, which is called weight decay. Is that really important? It turns out it is important, but if you ignore regularization, you automatically get regularization, interestingly, in non-convex optimization. So it turns out if you want to minimize an unregularized objective, which is just the training loss, and you look at gradient flow, which is the limiting case of gradient descent when the step size goes to 0, it is a differential inclusion, right? It turns out under some conditions on data, here we need the data to be separable over two classes, and we need the loss to be the log loss. Then this gradient flow, we can show that it converges to a solution to our convex program, which is minimum sum of L2 norms subject to separation constraints. So essentially what this shows is that as you remove regularization, actually what it does is it finds the minimum norm interpolation version of the convex problem. So it still has the same convex regularization going on, which will give you solutions that are quite sparse. Although in the original formulation, there's no such regularization. It buys you automatically, right? And this is very similar to gradient descent conjugate gradient. If you initialize at 0, they will find the solution given by the pseudo inverse, the minimum L2 norm solution, right? Although you don't add any L2 regularizer, they have that tendency to pick minimum norm solutions. And just like here, we find the minimum L2 norm in the parameter space that corresponds to minimum sum of L2 norms. So the interesting thing is you get a sophisticated regularizer, sum of L2 norms, which will make solutions sparse, which will induce structure for free without using any regularization, right? And I believe this is happening in deep nets trained without any regularization. They still find structure solutions because of this fact. Okay, so how do we train deeper networks? So one way is actually you break down the training problem into training a single layer at a time. And people show that actually this method, the layer-wise learning method, it is comparable to the state of the art. If you train a 16-layer neural network, this VGG16, this is one of the good performing ones, you will get these accuracy values. If you train them layer by layer, using non-convex optimization, people show that you get comparable accuracy. So one way forward is actually you use convex programs, and then you build your deep neural network single layer at a time or 2 layers at a time using the convex program. That's one option. Another option is actually you can train jointly 2 layers. I will show you 2 or more layers, 3 layers, 4 layers. It is also possible with convex program, but there is an issue. I will talk about that. Before that, let me tell you about generative adversarial neural networks. So these GANs are used for generating fake images, fake samples. And there are 2 neural networks. One discriminates whether it's real or fake, and one generates the images. And it is usually formulated as a saddle point problem, minimize, maximize, some objective with respect to generator and discriminator. It is a non-convex saddle point problem, but the maximization problem, minimization problem, they're both non-convex. But if you actually take our framework and convexify these neural network problems, what you get is a convex concave game, right? And we have much better results for convex concave games. In certain cases, we can solve them exactly, or we can analyze the properties. So here we can actually take a 2-layer generator, 2-layer discriminator model, specifically with ReLU generators and quadratic activation discriminators. And we can solve this case exactly to global optimality with convex programming. And turns out the solution is the generator problem is closed form and discriminator problem is given by a convex program. And we tried out this method just to see how it does in practice. And we use the layer-wise training approach. This is called progressive GANs, also used in the literature. You start with lower resolution, you train 2-layer generators, 2-layer discriminators, and then you make them larger in size, and then train 2 more layers, and your generators and discriminators, they get deeper and deeper. So it turns out with convex optimization, using this data set, you can generate some faces, not as high as state of the art, of course, but just to show that the basic idea works. This is the way how each image is hallucinated by the neural network, right? But with the convex program, we have a much better handle on what exactly the model is doing, and we can actually optimize it faster with our methods. Okay, so finally, what happens if you have a deep network and you want to train it jointly over all the layers, or 3-layer or deeper, right? So we will have one more ReLU layer here. So again, it turns out there is a convex program, right? The regularization is sum of Frobenius norms. And here we have a double sum that looks like sum di dj. These are what we call double hyperplane arrangements. Since we have 2 ReLU layers, we have to look at the possibilities you can have in data separation in both of these layers, right? This di dj, there's a definition, but it is just like before. Enumerating all the IDJ is hard, and we will have lots of variables. So it's not very practical to solve these deeper neural networks with convex programs. But it is nice to know that there is a convex program and the solution will exactly match to the non-convex one. And right now we are working on better ways of solving the convex program. So we know the solution is very sparse. There are lots of variables, but the solution is very sparse. We are investigating better methods to solve it, knowing that the solution is sparse using active set or homotopy like methods. But by random sampling, you can solve it approximately. you can randomly sample DI and DJ, as I showed you before. And turns out all the ReLU network problems will have convex programs. They might be larger in size. They might have lots of variables, but there is a convex program that will match in value and also in solution. You can generate the solutions from the convex programs. So let me conclude here. So the main result is that ReLU networks can be trained in polynomial time. We have some extensions to polynomial neural networks as well in the generative adversarial networks paper. We can apply convex optimization solvers and, more importantly, theory of convex optimization, right? For instance, analyzing the sensitivity of solutions, finding better upper and lower bounds, diagnosing the solution, making the solution more robust using robust optimization. All these are possible. Even if they're multi-layer, we will have convex programs. And I think the key takeaway message is that neural networks seek sparsity, which is not really evident, which is not obvious in their formulation. They seek this block sparsity, which is looking for the most concise model that will fit the labels, right? And with that, actually, it's not surprising that deep neural networks generalize quite well. Although they can have tons of parameters, they are actually looking for the simplest model that fits data. And an architecture search is like a regularizer search, right? Whether it's block L2, L1 norm or nuclear norm, by tuning the number of neurons, we are actually searching the right amount of regularization. And the code is available on our webpage. So if you want to regenerate the figures I showed you, you can find the code. And right now we have interior point off-the-shelf solvers, and we have a PyTorch model as well. You can try those out. So that was all. Thank you very much for your attention. I'd be happy to take more questions.
Thank you, Mert, for this very, very interesting talk. So are there any questions from the audience? So we have some questions in the chat, some new questions. Yeah, there's a question by Johan Tobias Sheikh.
Okay, I can read. So yeah. The question is, solving the GAN pair exactly means, what does it mean? Doesn't that just result in the discriminator and generator just learn the training set exactly? Okay, very good question. So if we go back to the GAN slide, what does it mean to solve it? So we have a min-max problem, right? Solving it exactly, what it does is you find the solution to the max problem, right? The max problem will be the solution of a convex optimization problem. So just a second, right. Okay, so what does it mean to solve this exactly? So this maximization problem, right, with respect to a neural network, if you plug in the convex program, this will be some maximize some concave function because it's in the max formulation, right? Minimize minus convex function. So maximize some concave function called that C of theta. This we can solve using convex programs, right? And then we have min, max. Solving it exactly means we solve this maximum exactly. And then the value we can minimize with respect to theta G exactly. And if you're thinking that this will not be a good approach.
So I guess there is a more direct answer. So we're talking about saddle points of a coupling function. So these are the solutions, the so-called saddle points.
Right, we find the saddle point, but I guess the question is whether it's a good idea to solve it exactly.
Okay.
I mean, maybe not. I mean, the non-convex methods are not solving it exactly. This was the reason actually we made these experiments. So these faces are exactly the saddle points.
Yes.
And they show some nice patterns. You know, these are not really high quality because these are a bit shallow, but you see these fake images, you know, generated by this approach, solving the saddle point exactly. Right. Local methods actually, they never converge. They never converge. Maybe they oscillate around the saddle point, right?
But for convex concave games, yeah, you can expect to detect the saddle point. I mean, this is.
Oh, right. But in the non-convex formulation,
of course,
you don't see convergence. Yeah.
But then one has to just adapt this notion to that setting. Okay, so let's take another question.
Right. Another question is, ReLU seems simple, but makes the training problem non-convex. That's right. Is there an activation function which seems complex, but does not make training problem non-convex? If you have a two-layer network, regardless of the activation, it will be a non-convex problem, right? So if you take this phi function, anything like a linear function, if phi of t is t, still it's a non-convex problem because you have a product of two weights. Right, so it's always non-convex due to two layers.
So Mert, so we have a question from one of our colleagues in the room, Timu, and then we can continue with other questions in the chat. So Timu.
Yeah, thank you. You mentioned the possibility of training a deep network 2 layers at a time. I was just wondering what kind of data, what's the training set you use for those internal layers?
Okay, that's a very good question. So this layer-wise training approach, it's actually proposed earlier by Bielowski et al. What they do is they take the data set, okay, and then they train a 2-layer neural network. Okay, so this is training data, it goes in here, and then you train 2 layers and you fit the labels. Why? Exactly, at the end of 2 layers, okay? And it gives you some representation, you know, some hidden layers, some second layers, right? You take this hidden layer and then you train 2 more layers on top of it and you predict the same labels. That is, you always predict the target labels.
Yeah, that
labels
was
Y.
Okay, thank you.
Sure.
Thank you,
and it's not obvious if this is the best approach. I mean, you're always trying to fit to the labels. There are actually alternatives in the literature. This makes it a bit too overfitting initially, because a deep neural network doesn't give you immediately the labels, right? But this approach, you are actually forcing it to give labels directly. And in the literature, there are better proposals than the labels.
So just to check if I understood, so you start with the first 2 layers, then you get some outputs after training. Are those outputs then what you use as inputs for the next 2?
Oh yeah, exactly. Yeah, exactly. And these are usually convolutional neural networks. The first layer gives you lots of filters, right? You convolve your training set with those filters, and that is the training set for the next stage.
Good, thank you.
Sure.
So there is a question by Tingwei Meng. He's asking how to proceed with the K layers, if one can do the same by considering K-1 hyperplanes.
Okay, good question. Yes, it is possible. We did this, well, only theoretically for now. It will be essentially like this, right? But you will have K summations here. If you have K layers, it will have K summations, and then it will have DI1, DI2, DIK, right? And theoretically, you have to enumerate all of these diagonal matrices, right? In practice, you can sample randomly, but again, the problem is you will have lots of variables.
Yes.
Although the solution will be sparse, it is challenging for convex optimizers to solve this problem.
Yes. So there's another question in the chat.
Okay, there is another question. Linear is non-convex because 2-layer linear is equivalent to 1-layer linear. That's right, a 2-layer network with linear activations. Have you looked into residual networks or its continuous limit neural differential equations for training deeper ones? Okay, good point. So residual networks, we haven't looked explicitly, but it is a simple variant because this is the 2-layer version. If you have a skip connection, right? ResNets have skip connections. It will have this term plus X times something like X times UI minus VI. So this is doable, certainly. And it might be more stable doing it this way. The limiting case, neural differential equations, that's a good point. We haven't looked at it.
Okay. Matthias?
Yeah, thanks. Just out of curiosity, so the quadratic regularization terms, are they somehow chosen by some theoretical reasoning, or are they just a guess that you make here? Because, you know, from statistical perspectives, there are also different penalizations and regularizations you could take. Even LP regularizations are used in statistics where the P is between 0 and 1, so even non-convex regularizations. So I'm just wondering what actually triggered you to make this choice for the regularization?
Oh, okay, very good question. So the reason why we look at this regularization, sum of squares of all parameters, is that in the neural network literature, this is the most popular one. People call this weight decay regularization. You're right, you can change this to anything else, but with this weight decay, you get this nice connection to sum of L2 norms. And then moreover, this was actually just a guess. Since this is the most popular one, we said we should analyze this one. But later, if you look at this result on gradient flow, right, which I showed you, you get that regularization automatically. So if you have 0 regularization, you apply non-convex gradient flow from random initialization. The solution you find is the one that will minimize exactly that regularization, right, which will become sum of L2 norms subject to separation of the classes. So this shows actually this is the most natural regularization if you just want to optimize the neural network. But if you want something else like sparsity, then of course you can do sum of L1 norms or something else.
So thank you, Matthias. We have another question about convexifying learning problems.
Okay, so the question is, do you have an idea how to convexify learning problems of other neural network architectures like convex input neural networks, where the output is a convex function of the input? Okay, good question. So these input convex neural networks, you can convexify them, although we haven't done it. It won't be too hard. Essentially, they only have the restriction of non-negative weights, as far as I know. So you want these W2s non-negative. Yeah, you can include these constraints to the convex program, and you can convexify it. That's doable. But the other question, can we use this convexification framework to convexify other models? Possibly, quite possibly. The critical aspect here is that we have a sum of hidden neurons, right? Any other machine learning method that looks like a sum of this form, you can apply I think our framework and get a convex program, right? So anything that looks like this, other than a neural network, you can apply the framework and get convex programs. But one critical aspect was the ReLU activation, which acts like a 0-1 filter, right? That has to be that way, right? Otherwise, if you have sigmoid or something else, this result will not work.
Okay, thank you. Are there other questions?
I have one quick one.
So
you seem to have those L2 norms throughout, but does it really matter if you change them with any convex functions? Would your convex reformulation still work?
Okay, good question. So if we change this to something arbitrary, like R of W1, W2, which is convex, the convex formulation will not work. It will not work. It was actually critical to have this sum of squares. Yeah,
how about
the
loss function?
You mean the loss function?
Yeah, can that be arbitrary convex?
Oh yeah, loss function can be arbitrary convex. You can have any convex loss, right? It just carries over directly. So here we have the squared loss. It just carries over here exactly. Here we also have the squared loss. It could be, you know, hinge loss, logistic loss, any convex loss you want. It is possible.
Very good. I just wondered, now that you have this convex formulation, you have a, like you say, you can have arbitrary convex loss function, but in the convex formulation, it would make perfect sense to change the L2 regularization by other regularizations. You would still have a convex problem. What's the interpretation problem?
Okay, another very good comment. Yes, after you get this convex program, right, you can change this regularization to a P norm if you want. P norm. Exactly, right. If you use L1 norm, it will give you additional sparsity. The coefficients UI will be sparse. Or you can have something like L infinity norm if you want. most of the same values. It is definitely possible. You can use total variation if you want.
Okay. But you're saying that
Right.
you're saying that you lose the connection to the non-convex problem.
Oh, yes, that's right. So if I change this to, let's say, total variation or something else, possibly it will correspond to some other non-convex regularization that you can figure out working backwards from theory. But I don't know. You lose the connection, looks like, but maybe you can recover what's the original regularization that will result in to the regularization of your choice. Yeah.
Because it looks like the convex problem still makes good sense. Maybe that's
right.
the right formulations to start with from in the first place.
Right, maybe, yeah.
Thank you.
Sure. Another question from the chat is, does this convex version approach give you a straightforward method how to robustify training with regard to bounded adversarial noise? Okay, good question.
This is the GANs approach. It's very similar to GANs. It's also a min-max problem at the end.
Oh, right. It will be similar to the GAN approach. I think so. I think this will just look like robust convex optimization, right? If you minimize with some data uncertainty, there's work by Nemirovsky that shows you can actually solve the convex counterparts, robust counterparts of convex programs, right? That is one approach. If you have data uncertainties here on X and Y, you can actually, this is an SOCP. The robust version will be probably also an SOCP. You can solve that. Or you can solve a chance constraint probabilistic version. It is all doable, I think. We haven't tried it.
Okay,
right?
thank you, Mert. So I have a second question on this convex problem, in particular on the solving of this problem. So let's forget about P. So let's take the initial formulation with the 2 norm. Okay? And here we're talking about an objective function which is non-differentiable. And then you mentioned integral point methods, but of course these are not the most appropriate methods for such problems. Yes, is
right.
Yeah, you would have to calculate the derivatives of these functions, and you can get some troubles. So so for this type of problem, if you forget about the feasible set, one would just apply so-called proximal gradient methods. Evaluate the norm by the prox and then make a gradient step, or the other way around for the smooth term. But then you have constraints, and these constraints are inequality constraints, and
right.
complicated constraints. You have also matrices there.
Right.
But what is nice to see is that the variables ui in the right-hand side of the objective, and vi as well, and in the constraints are separated. Is it correct?
Right.
And they are linked only through this smooth term. And then one could try to use, of course, primal dual methods, but block iterative, so which update just one, let's say, one part of this whole vector of variables, and in the random way. And then I guess this will be very efficient. You don't have to make a full update in every iteration, but just to pick some coordinates and to update these UKs, VKs, and then if one can do this in a clever way, then one gets a very good method for this. So I guess there are methods which are much better than integral point methods for solving this very interesting convex problem.
I would guess so. Yeah, I would love to learn more about those. Yeah, I agree. Yeah, totally. ADMM is another good approach that we haven't tried, right? Decoupling the blocks using ADMM.
Yes, for instance, this is connected to ADMM primal dual. I mean, these are all related. Yeah, and there are very good methods which are also emphasize the sparsity. You mentioned several times, and which of course it is in the objective function. Okay, I mean, like from the point of view of solving methods, I guess one has many good options.
Yeah, that's great to know. I would love to learn more from you about that.
Great, Matt. Are there other questions? Okay, Matt, let us stop here. So it was a great talk. So we had a fantastic discussion. Many colleagues in the room. So thank you very much. It was a great pleasure to have you in our seminar. So just like to announce that we will post the video and the slides on our website. and that our next speaker will, oh, we would have another question. Okay, yeah, let's take the last question. Last question. Johan Tobiaszek. Could you please ask the question, or yeah? So, okay, so we have it.
Okay, the question is, in neural networks applied to control tasks, one approach is to check that the system and the control satisfy Lyapunov's second method for stability. This is currently done using mixed integer programming to find counterexamples to train on. Can this be accomplished using simpler approaches? Oh, okay, I think so. I think so. Instead of taking this non-convex formulation, if you start with the convex formulation in the controller, I believe that you will have simpler conditions if you want to verify Lyapunov's conditions. I think so. We haven't looked at it, but I think it is possible because this formulation is much simpler. It essentially decouples the combinatorial hardness in the problem, which is about enumerating these patterns, and the continuous hardness in the problem, which is actually just a convex program. I guess so. Yeah, I think you can do better Lyapunov condition checking. Okay, yeah, great comment. Thank you.
Thank you. Thank you very much. Thank you, Mert. So we stop here.
Thank you, everyone.
So have a nice week. Next speaker will be Mindao from Australia. Yes, next Monday, the same time. Have a great week. Wish you all the best.
Bye.